Alrighty then. All right. Well, that was a decent enough clap to be acceptable. But yes, yes. All right, today. Oh, by the way, hey guys, what's going on? Memes here. Yes. The random dude in a yellow shirt and gray sweatpants on the internet is gonna postulate something. We're gonna notice a massive coincidence, and we're going to lay it out here because this is something I've been working on for a little bit now. And you notice little coincidinks and everything. And it's kind of like, oh, look, you do these things, the electric constant, the magnetic constant. Oh, we do one. Oh, wait, look, we're getting the speed of light. Oh, that's kind of very interesting there. And the benefit of actually having time to spend and think about these things and go down the wiki holes, the Wolfram holes, gaining little bits of information by just random, like almost throwaway marks from like some of the smart people that we hold up and we revere. Why? Because they're very smart and they've done different contributions. And heck, even if it wasn't a fundamental contribution in some respect, it's like the ability to teach and provide knowledge, to pass on knowledge, skills, ingenuity. Well, I think that's the story of humanity. And that story is to level up. I am not wearing that shirt. Yes, I'm wearing what we were talking about yesterday that I should have been wearing yesterday. Yes, our hyperbolic partition equation, or this was the original, not with a J version. So I'm going to let folks start to roll on in because I'm going to share the paper that I've been working on. And again, it is not fully done. I need to go through all the acknowledgments and everything, but at least the primary calculations and everything we're going to go over today, can double check my work and everything and make sure that this isn't just a crazy person on the internet, but maybe a crazy person that had noticed something interesting. And again, might be nothing at all statistically. It is probably nothing. It is probably just a coincidence. But it was enough coincidence that happened to match with a lot of the data that I thought was worth exploring. And seeing as I'm not a professionally trained physicist, I have not gone through all that stuff, done a PhD and all these fancy things. No, I'm a dude on the internet, like many of y'all out there. I was very passionate. And maybe like another a good few folks out there. Maybe you got done yelling at the TV and you're like, all right, I'm done yelling at the TV. So I'm going to come online and I'm going to fix the world. We're going to solve all the world's problems. And then you're completely beat down by the world of politics and you realize, is anyone actually trying to solve any problems or they just want to yell at each other? Listen, if people want to yell at each other, that's totally up to them. They can do that. I thought this was perhaps a better use of my time. So as we're going to let folks roll in here, we're going to erase the board because we're going to go into a different realm. Well, not not really a different realm, just perhaps a different perspective using very similar things. Actually, I don't even need to erase everything here because I'm going to use some of the stuff that's already here. So folks roll in. But one of the reasons why I named this stream because I am very good at procrastinating, maybe a master procrastinator. Because all of a sudden I'll start doing something. I'm like, oh, here's a shiny thing. I have a question. Let me look at it from this perspective. But I figured if I actually said we're going to go over a paper I've been working on, well, I should probably actually at least finish the main part of the paper. So at least the calculations are done. We have some error bars and everything. And yeah, we'll be able to go through and parse these things best we can and see if it makes any sense at all. Because, well, to me, I'm kind of like I'm a big kid. You give me a puzzle, and I might be the kid that's looking there at the puzzle for a while, and I'm completely bewildered. I'm dazed because all these smart people are saying all these smart things. And I'm listening, and it feels like there's a bit of drool coming out of my mouth because I'm so perplexed and amazed. And then all of a sudden, it's like, well, what about that? Can we put that piece there? It's like, what are you talking about? Nobody's put that piece there. I don't know. It doesn't fit. Well, it's within a couple sigma of this, and it's like point 0.2 sigma of this. And it seems to maybe be able to explain a lot, but I digress. And we'll get into it now. So I'm going to erase everything up here except our formulation for alpha that we went over yesterday, the fine structure constant in this form. Okay, so alpha, we got our little Jesus fish style sign over there. So we got our alpha fish, and our alpha is defined as elementary charge squared over 4 pi h bar c e naught. What does that mean? I don't know. Something about charge squared. That's going to give us a dimensionless number. So somehow this 4 pi action at the speed of light via electric permittivity of free space will give us a dimensionless number. To cut the crap, so to speak, it's elementary charge over the Planck charge. You can square this whole dang thing, and you're going to get the same thing because it is computationally equivalent there. But oh, hey, Jax, there's it's okay. It's okay. Hey, we all feel pain. I think that might be the one commonality through humanity. But I'm not sure what to make of that. But what we're going to make of this is we're going to use this same this inspiration from alpha, and being able to take something that's more complicated and computationally reduce it into something that's more simple. And a lot of folks, there are a number of folks, they know about this. Why? Because it just comes out from the math. So people have known about this. John, oh God, it's something like John McCracken or something. I know it's not McCracken because McCracken did the little intro for myself and Fizz. Um, but we're going to take the same inspiration. And today, we're going to be talking about the Higgs boson. Specifically, its mass. I know Mike had popped in a little bit earlier. Mike Perone, I believe he's been working on a paper with David Chester upon, oh God, what was it there? Something about a fluidity, and they were leveraging something from superconducting research. And I'm looking at this, I'm like, oh, this seems to make a lot of sense there. I got like 1 over 2m, blah, blah, blah. Okay, we get this charge squared and everything, and then part of it, there's some electron charge, and I'm like, well, wait a second, are they doing that as an electron charge because there's a minus sign there? Will we use a different convention if there's a proton? I haven't looked into it that much. We just skimmed the Wikipedia article. I'm like, okay, this seems to make sense. But I can't say as far as superfluidity or some reimagination of Maxwell's equations, maybe something like that would come out for this. I'd love to talk to you guys about it, but we're going to be going over the mass component, or more specifically, the mass energy component, which may be able to tell us something here. Okay, so if we get this for alpha, all right, how about H bar? All right, excuse me, the Higgs boson. So the Higgs boson, and we're going to be looking for the characteristic of its mass, or mass energy equivalent. Okay, so this is a dimensional flavor, so we're going to be looking for its mass. I'm going to underline it because it's important. Okay, so Wolf's playing around, and actually a lot of this inspiration came from, oh God, it's Professor Sean Carroll's Mindscape with, I forget your name again. I'm so sorry. I highlighted you in my video, but the doctor, she had brought up that while working on particle physics research, if you're looking at the relationship between like the Higgs boson and the Planck mass, so if you got like the mass of the Higgs over there, and you put over the Planck mass over there, you're going to get about a magnitude of about 10 to the minus 17. But actually, the number we actually care about is, if we square the whole dang thing, that's going to give us, we're going to get a few significant digits here, approximately 1.05 times 10 to the minus 34. This is the mass unmasked term. The dimensions cancel out. So this is the dimensionless number here. Now, for those of you that may have been doing physics for a while, or going down some very deep Wolfram holes, so to speak, or spent a great deal of time looking at things on CoData, you're going to recognize this number. These are the first 3 significant digits of H bar. h bar being the reduced Planck's constant, or the elementary unit of action. So I'm going to draw a little arrow over here because we have a question. We're going to do our little H, a little squiggly bar there. And there's a question mark. Why does it match the first three digits? And you look at this and you're like, all right, so it's probably a massive coincidence. Okay. It's a massive coincidence because there's mass in there. I may have misspelled that, but that's okay. Let's spell checks for in our documents. But okay. So we have this massive coincidence, and you're like, okay, but it's like, it doesn't have all the digits because this we defined back in 2019 to 10 significant digits. Why? Because we had 12, but the 11 to 12 digits, we kind of had some pretty big error bars there. Okay, since we had those big error bars during the 2019 redefinition of SI, they just lopped off the last two, and now we just have 10 significant digits. All right, so we've got this, the 10 digits. Okay, if we got this to 10 digits, all right. And the Planck mass, we have, by its calculation here, we have this, we've got it to 5, and we've got it to 7 with error. Okay. With error, so we've got 5 digits that we know on this. We've got 10 digits that we know on this. The interesting thing, and the reason why I thought this was worth exploring, is because we do have 5 significant digits depending on the measurement there, but you look at it, and we're using data from Atlas, the Atlas experiment at CERN, and then we've got the CMS experiment, and that's putting it at 125.11 GeV, and then 125.35 GeV, respectively. Okay, so this is our experimental measurements. This is what we have from the Large Hadron Collider. It's different experiments. We've spent millions of dollars on that, and then we found the Higgs, or at least something that appears to have the characteristics of the Higgs that we were looking for. Okay, it happened to be in the generalized mass range. Okay, now if you notice from these two numbers over here, they differ in the last 2 digits. And I'm sorry, I should put the error over here. So the error in the Atlas, basically 11 in the last 2, and then the error at the CMS was 15 in the last 2. And again, they're pretty close together. It's roughly about a quarter of a proton mass energy equivalence, because a proton's about 1 GeV. It's like 936-ish GeV, maybe 38. Excuse me, MeV, mega electron volts there. Oh, hey, magnitudes matter, folks. But okay, the thing is, what digits do we have in common? I got the first 3. The first 3, maybe it's 124, maybe it's 124-ish on the upper side, because there have been some measurements, and we'll be going over some of those in the paper as well. But if you notice, okay, so we've got confidence, pretty dang good confidence, via tens of billions of dollars in the first 3 digits of the Higgs boson for these 2 most recent measurements. Okay, so if there was to be some there, so to speak, might we be able to leverage our information? Because if we got 3 digits for the Higgs boson, we got at least 5 digits, 7 with error for the Planck mass, and we got h bar defined at 10 significant digits. Is it really that crazy an idea to be like, well, what if we rearrange this, listed the Higgs as an unknown factor, and we solve for X? So we did that. And what we get is we invert this for the sake of notation, because rather than having to divide and everything, I think it makes it look prettier. So what we do is we flip it around and we go Planck mass m sub p over, oh, excuse me, we're going to do energy. So just for sake, and it's easier to remember, you do the c squared thing, you convert this to energy. Basically, you take the Planck energy. So we're going to do E sub p. And then we're going to solve for x. And since this is an energy equivalent, we would like it in GeV, giga electron volts. So billions of electron volts. Because again, the unreasonable effectiveness of electron volts, I would claim. I guess that was supposed to be a joke. Probably not that funny. But all right, so we got the Planck energy. We're over that. And then this was a square term. So we square it. And now all we do is we just throw in, we multiply it by h bar. And we believe it's supposed to be precisely h bar. So since h bar is an action, it's energy per second. So we're going to cancel out the energy, or at least one-time thing. So it's going to be a unit of action. So that's expressed in joule seconds. So we're going to do 1 joule second. Cool. And then when you solve for x here, this is going to give you mass of the Higgs, m sub h, of 125.37 GeV. Okay. Now this is where I need you all. Now, okay, this number, if we do it in this expression, which again, the inspiration for even trying something like this was this computational reducibility for alpha over here. Because basically, again, alpha is normally defined as elementary charge squared over 4 pi times h bar times speed of light times the electric constant. You can reduce it to elementary charge over Planck charge or boundary of charge, and you just square the whole dang thing, and you're going to get alpha. Okay. So we're basically doing the same thing, except the elementary charge, we're just doing the Planck energy, and we're solving for something right here. So we have our xGeV here. We have our same squared format. We're just multiplying it by h bar and then just trying to solve for a thing that would be 1 in those units, which in this case is joule seconds, units of action. Okay. And that gives us an estimated mass of the Higgs, or its mass energy equivalent, of 125.37 giga electron volts. Okay. How does it compare to our, I think, oh, excuse me. Error. Do 1. There we go. Hey, we want to be open. We want to be open. And it's like, you got these measurements, you got these error bars. We're supposed to do the scientific method. That's the whole point of putting it into a paper. So you're actually putting it there, and rather than just rambling and hoping you're right, you do the calculations, and what does it come out to be? Okay. We got our 2-1 there. How does this compare to our most recent measurements? All right. So if we subtracted 2-1 there, we go to like 1-6. All right. So that's a little about 1.5 sigma of the Atlas over here, because we got 125.11 GeV. And then we got error of, well, actually, if it goes up, actually, it is within, yeah, because that's going to bring us down. Okay, so technically, that is why we do the error bars, right? Okay, you can tell I just finished literally the error notation for this probably about 20 minutes ago. But all right, and we get the CMS, 125.35 giga electron volts. That's really dang close. That's really dang close. See, I had seen some of the more recent Atlas ones, and like even Atlas, I think one of the last ones was 124.98 GeV, and I think one of the early CMS ones was pushing 126 GeV, but it seems to be right in this range right here. About 125 GeV, it appears to be in the lower half there. But this Just even without any error bars right there, it's about like point 0.2 sigma, something like that. Uh, maybe a little better, but that was one of the inspirations for actually going through and doing these calculations, just because it seems to be well in the ballpark. Okay, what what the heck does any of this actually mean? Because I was just doing this literally puzzle pieces. Oh, I recognize this value. That looks to be about the value of H bar. Let me put in H bar. I put in the Wolfram alpha, and then it comes out to, and again, it has some error there. It was estimating at 1 joule second. I'm like, 1 joule second? I remember a long time ago, Thad had really expressed the importance of what is one. Now, I don't have an answer for that, but anytime I see one of something, maybe that's worth paying attention to. Because even just with our standard dimensional analysis of stuff and things with our Planck constants, yeah, the Planck charge, that's a one. The Planck time is the one of time. The Planck length is the one of length or spacing, depending on how you want to raise it to its different dimensionality. That's easier when we raise it to higher powers for us to kind of understand, well, at least up to 3 dimensions. And once we get to 4, it gets a little wonky and our minds start to go off in ways. And I'm going to stop talking because we're not going to promote entheogen use on this show, at least right now. But ultimately, we have those ones. Planck mass is a one of mass. Yeah, and then Planck temperature is a one of temperature, which happens to be a very ginormous number. So these are the things that get the old noggin a jogging. Okay, but when you said equal to 1 joule second, the interesting thing that we had even gone over the other day is if you just take the relativistic mass of 1 joule, it's actually the factor of c squared. I'm like, well, that should just be an obvious thing, but it's like, duh. Or Rick put it pretty eloquently. He was like, it is 1 in parenthesis c squared. Because 1 is probably a very important thing, or at least that's what I'm claiming right here. So we should be consistent with our framework. All right, we've got some few more folks that are joining us. Let's sit down, see what we got going on. Oh my God, all this all this different stuff going on. All right, we got Grizz. Um, now, okay, so Grizz, as far as an infinite field, now when you say infinite, we have to be careful with infinity. We're talking about infinity in space. Again, that might also how you define those things. I'm thinking our realm, what we colloquially refer to as universe, I would claim is eternal in time. So maybe you could use an infinity in time, at least. And again, maybe there was a beginning and everything, according to the calculations. It kind of looks like maybe there was, listen, outside of where we live here, there be dragons for all I know. Okay, that wasn't a super satisfactory answer. But let's see. Yes, we are wearing a traditional yellow shirt here. That's totally fine. Yes, Mark. Yes, a coinky dink in science. I mean, that's never happened before. It's just you just sit there, you look, and again, here's the thing: if I didn't have access to something like Wolfram Alpha, shout out to Professor and everyone at Team Wolfram that's contributed to that over the years. I wouldn't have known what to look for. If it didn't say 1 joule second right there, it's like I may have been like, oh, okay, that's kind of interesting. Blah 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 blah. It's otherwise I'm just like, it's just a straight coincidence. Uh, I'm yes, I am almost did it a paper nerdy. We're almost. I at least have the main calculations. We'll go over there in just a minute. I just again, a lot of these are just practice for me, so I can actually go through and explain things. I remember the first time I was ever here, and then Thad was like, I had asked a question, and then he's like, "Here you go. Here's a marker. Go up to the board." I'm like, "What the heck do I even say?" And I'm so messy and everything, and now my penmanship is slowly increasing. I should probably actually sit over here. Thing is, we all saw that yesterday, and if we're going to try to imbibe new information, especially someone that clicks on it, Higgs boson, what are you talking about alpha over there for? Okay, but it's one of those things where if you haven't done it before, and you might have the most crystal clear picture in your head. Like a lot of, I felt like I was writing the paper while I was going to sleep at night. I'm just going over through certain phrasing, but it was phrased in a very particular way, and it was more. I'm gonna have to do. What I'm just gonna have to do is just start these different talks that I give. I should probably do like a little summary and actually update the Physics Monastery website and do like a little blog so I can verbalize things. I can write things. Some people don't want to have to sit through even at multiple X speed. Some dude that's rambling on. It's like, listen, I'm interested in the topic. I can't stand your voice. Let me just go through a little, either a transcript or just, I don't know, a couple of paragraphs on a website. And I understand people consume information differently. I'm very auditory based, if you couldn't tell. But yes, yeah, we're living at the speed of human. About the secondish realm, about the meterish realm, and dozens of kilograms ish realm. It's very interesting. Uh, have I seen a storm at the speed of the cat? Oh my God. You think a Tasmanian devil can do some damage? Had some gashes. My dad, God rest his soul, he got cat scratch fever and stuff back in the day. But listen, there's a lot of sus things out there. Sus, but verify. That sounds appropriate, right? What is one? Yeah. It's um now to, I don't know, maybe should we listen for light? Is that the inverse of that? Something along those lines? Uh, what is one? It's Dad proposed that to me because I still remember. Oh, what was that? It's we're gonna play that. We're gonna play that. We can take a copy strike or something. Let's see. Just because it was so fantastic. It was the first time I interviewed Thad, and this is where you start getting the philosopher side out. The one, I think. Let's see. Da-da-da. Ah, here we go. Prime and back again. Hold on. Let me bring this up for the class. Give me a chance to grab a drink. All right. Okay. Yeah. Prime and back again. Discussing the one. Here we go. This should be good.
The question of what the primes are. Do you know what the definition of primes is?
Is it? It's a number that's only divisible by one in itself, I believe.
Exactly, by itself and one. All right. Why do we include one?
I thought we didn't include one.
No, we do as part of the definition.
Is it?
Yeah, you just said it.
No. Okay, the reason I did the reason
divisible only by itself and one, but dividing by one doesn't do anything, right?
You're gonna. I feel like you're gonna tell me it's gonna do something now. Okay. And for some reason, he said we don't count one as a prime, so I just took that as gospel, literally because I heard it probably about an hour ago.
Sure, but the definition of
As I start sarcastically responding, waving my hand, and I'm still completely muted. Nobody has ever done that before. Long story short, I think I listened to a number file and I heard that. I'm like, oh, okay, I guess that makes sense. And I took it as gospel because I was a very smart person saying something. Thad rephrased it. He's like, all right, so what if you could think of one as a prime, but rather than the first prime, what if it was the 0th prime? We continue.
Any prime is being divisible only by itself.
Okay.
And I'm asking, why would we insist that we include the one if dividing by one doesn't do anything? It seems like meaningless information to attach to your sentence just to make it longer. The one has always been a big mystery in math. I mean, if I were to wrap up in a really short paraphrase version of what the question fundamentally still is in math, okay, it's almost parallel to the fundamental questions in physics. It's, what is the grid? What's the space that we're mapping? What is this XY in which all of these rules of math work on? Okay, that hasn't been explained. It's a big, huge mystery in question. And the interesting thing is that the grid, we know that there is a grid when the math's all working. We know how much levels of math are working. We have plus and minus that are allowed operations and symmetric multiplication and divide, except for the point zero, everywhere else it works, right? But every other operation we add, we have to make a new exception. Okay, there's an interesting, the grid doesn't allow these operations to be perfectly symmetric everywhere, but they work most places. So we have to make sense of why this math works on this metric. What is the actual metric? Well, some people would like to say, well, if we could find a way to twist the metric so that it's making sense, right? Then
Okay, so this is literally the point where you went into, what if we were to twist the metric? What if there was a way we could go about that? Well, my friends, let's wrap this up.
it would make more sense to make sense of the math. But if you twist a metric, then all of its points are screwed up, right? However, it's been shown that there are ways, interesting ways, to rotate a metric several ways so that its points, 1, 2, 3, 4, all the grid points stay the same, but all the connections in between don't, right? And what operator do we need to do that? The gamma function. All right, kind of see where we're going here? We have a hyperbolic figure eight knot. We've projected a domain, and pretend we're talking about a universe now that only has one of this balance involved, okay? There's nothing else. It's the simplest, just one of these, not our actual world that's intersected with many, many of them. Okay, in that balance, let's see, it projects, or if you're only looking at that domain, then that domain is a universe.
Wow, this is why I use the term realm. We were having a conversation a little bit the other day, and Dad was like, I feel like the best way, in order to figure this out, we just need to look at like the atomic scale, just the very minimal things to get a picture. And then we found this that interesting thing. Oh, it's the inverse of like the Z boson or something. Yeah, about the mass of Earth in kilograms. What? I mean, again, that must be a coincidence. And then it's like, wait a second, there do seem to be certain clusterings of mass, and coincidentally, the inverted mass scales for like I don't know around the levels of fusion for stars and stuff like that. It's like maybe we just got to look at it from all the areas to get the best view possible. Okay, I've bloviated enough. Let's finish this fun little thing.
And what's the balance point? What's the one? What's the reference frame most natural to that universe? It's the reference frame in the universe that's the most stable, right? That external projection is the middle action of the last boundary. So in the temperature domain, that outer rotation, the middle of it is just the one. The one what? The one compared to this system, the one of this system. Now, why do we care? Well, because the system is literally defining a one that decomposes a very specific ordered way. A geometry of decomposition of one. That's what the system defines. And if you want to talk about things that are allowed to decompose together uniquely, at minimum, they must balance at least with the hyperbolic figure eight knot.
Whoa, the chat is losing their minds right now. They're going, oh my God, not the gamma, don't twist the metric.
I thought that was very entertaining, but all right. Oh, hey Tom, good to see you, my friend. Thank you for joining. Okay, sorry. All right. So the main point that we're going into is, as far as the Higgs boson goes, we noticed a little bit of a coincidence, if you would. Sorry about the digression, but Mark had brought up something and it triggered something in my mind. The conversation about basically why I was looking for one. So long story short, we noticed a little bit of a coincidence because we got alpha over here, aka the fine structure constant. It's defined as elementary charge squared over 4 pi h bar c e naught. Okay, all that jazz, but we can computationally reduce it from this larger expression over here to simply elementary charge over the Planck charge, and then we square it. It might be a little hard to see because it's in. Okay, you can probably just barely make it out because there's a little bit of shininess over there. Okay, but these are equal. So by looking at that expression, one of the things was brought up on Professor Sean Carroll's Mindscape broadcast a few months ago. And again, I keep on forgetting the researcher's name. I apologize. I have her listed in the segment in one of the videos over. I think it's literally called A Massive Coincidence or something, or estimating the Higgs boson mass in an actual produced video. But basically, if you take the measured mass, and we have measurements over here, two of the most recent measurements of the Higgs boson mass are from the ATLAS experiment and the CMS experiment, and they are 125.11 GeV and 125.35 GeV, or giga electron volts, as its mass energy equivalent. Okay, so we have those measurements. And when you take those measurements, and again, we have about 3 significant digits. We have high confidence in 3 significant digits. The last 2, we still have error, and the experiments are, one's a little bit lower, one's a bit higher there, but we have confidence in 3 significant digits, I claim. Okay. So when you take the mass of the Higgs and you divide it into the Planck mass, basically we're doing a similar thing to we have over here for the simplified version of the fine structure constant, the computationally reduced form, because it's literally less computation. And you take the mass of the Higgs, divide by the Planck mass, we square the whole thing, we have a mass dividing into a mass, so it's going to give it just a dimensionless magnitude. That magnitude is approximately 1.05 times 10 to the minus 34. And for those of you that may have been studying physics or playing around or spending far too much time on Wolfram Alpha, looking at different constants in nature and their relationships, that magnitude is quite familiar because it's the first 3 digits of h bar. Now, we only have 3 significant digits right here because, well, I mean, we only really have confidence in the first 3 significant digits. So I looked at that, and not knowing any better, I'm like, well, what if the number was to come out was actually supposed to be equivalent to the value of h bar? What if that is the puzzle piece that is supposed to go in there? Okay, that's a hypothesis. Hey, this is what I learned in high school. It's like, you have some phenomena. You look at it. You try to think of something that might be there. You have a hypothesis. All right. You explore the hypothesis. And then eventually, if it's the best explanation you have at the time, it seems to fit with at least the data we have confidence in, it becomes a theory. And then if yada yada, if it holds, and it becomes a law or something. Apparently we don't do laws anymore. That's a separate rant. But okay. So we look at that. So what we did, for Tom and anyone else that's joining right now, just a quick recap, and then we'll get right into the paper. Basically, we took, just to have it in giga electron volts, you take the mass energy equivalent. So you take c squared. So rather than doing the Planck mass, you do the Planck energy. And we're going to invert this right here. Why? I think it looks prettier to multiply by h bar rather than having to divide by h bar. Personal opinion. You're going to get the same answer. If you don't, let me know. But okay, so what we do is, like the fine structure constant, it's reduced form. We take the Planck energy, okay, and then let's say we're going to solve for x. So rather than putting in the number of measurement for the Higgs boson, we're going to conjecture that using this expression, we should be able to solve and get a calculation for the mass according to this conjecture. Okay, so we do the Planck energy, and then we're dividing it, and we're going to put in x, giga electron volts, because it's an energy unit. We're going to square the whole thing, and we're literally just going to multiply it by h bar, Planck's reduced constant, the elementary unit of action, and we're going to set it equal to 1. And 1 units of action is joule seconds, because it's energy per unit of time. So when you do that calculation, to be fair, you actually get 2 answers here, because you could write this as an absolute magnitude over here, and you'll just get a positive answer. But doing it in this form, we do actually get two answers. So we get the same thing also negative. So we get 125.37 GeV plus and minus. So also minus 125.37 GeV. Believe I think typically we invoke, was it the positivity conjecture or something like that, where it's like, oh, we believe it, our mass will always be like positive and stuff. I'm putting this here just so it's out there. Who knows where we'll go? Who knows if it's significant or not? But this also has error bars going to my calculations of 21 in the last two there. And so we get an estimated mass of the Higgs from this expression of 125.37 GeV plus and minus, with error bars of 21 in the last two digits. Okay. So we compare it to the Atlas and CMS. It's like, all right, so, well, if you move that up one sigma, like, all right, so it's about 1.5 sigma from the target right there. If you move it up to that 125.22 and you move this down, all right, could be within the error bars. And then this over here, 125.37 versus 125.35. Pretty close. That's pretty close. And that was what actually helped give me the confidence, because I saw the Atlas number. I'm like, okay, it's kind of there, but and then this other one, okay, well, that gets at least another significant digit or so. I also didn't include it because they were older measurements, but I think one of the measurements out from, I think it's probably one of the early runs, like 2013, 2014. I think it actually was 125.37 GeV. So you, you can't call this a prediction because, well, I mean, if we've already mentioned it, you can't use it as a prediction. If one was to, and again, this is probably wrong because most things are wrong, but if we would like to verify or falsify, which might be more likely, this calculation, we're probably going to need a muon collider. We're going to need higher precision energy particle experiments. Because right now with the Large Hadron Collider, okay, you smash some protons, a proton, and antiproton together. It's like, if it's not an elementary particle as per the standard model and how we have it set up right now, we can get a lot of energy, but to reconstruct and see what might actually be our Higgs boson event, that's kind of hard. We're smashing some elementary particles like electrons or muons together. Electrons we can do really well. It's just electrons have a heck of a lot more less mass. So you need to get them really, really, really fast. Muons have a heck of a lot more mass, about 206 times more. The problem is they decay in like nanoseconds, something like that. There's maybe like a couple of nanoseconds, maybe microseconds. But apparently, we now have the ability to produce muons. We have the ability to actually start to put them into almost a beamform, and they accelerated up to, I think, about 0.8% the speed of light. Not as fast as we need, and then we're going to need precision equipment to smash them together. But we got a lot of really smart experimental physicists out there, and they're wizards. As far as I know, any sufficiently advanced technology is indistinguishable from magic. It's like magic to me. You look at some of these crazy machines and everything. But all right, I hope that was a decent recap. Oh wow, I'm missing so much. Oh, Dan is joining us. Thank you, my friend. I was thinking about you the other day. It's uh yeah, well, actually earlier I'm like, well, and we got K Show. It's good to see folks that you've actually seen out here in the monastery. I know Rick has come by well again and everything. Well, if we can create a black hole, that would be pretty amazing, because then we would have, I think, hit the Planck energy. I think we're many, many, many orders of magnitude off. I'm not going to say I haven't thought about it. I'm not going to say I haven't thought. And technically, according to the calculation, even if you did do that, the thing's going to probably pop out of existence. Okay. That might be a kind of significant boom because it's radiating out, I think, Planck temperature divided by like 8 pi or something like that. Um, but I'm pretty sure we'll be okay. Oh yeah. If anything, we should be more concerned about the potential neutrino radiation. That's I think an early paper talking about a muon collider was like, well, what are we going to do about the emergent death rays? It's like, what? Because if you're emitting a whole lot of neutrinos in the same direction, they're extremely high energy. The meme is you're going to have exploding cow and steak everywhere. Um, that could be a bad day. Apparently, if you had a little bit of like rotation or wobble to it, it's like, okay, get neutrinos, but now you have no concentration of that. Because usually any type of lethality is intensity, time, your exposure, and jazz like that. Um, it's okay. It's okay. I understand. There are some concerns. I think we'll be all right. Um, and to be fair, we could probably even just do this. I'm just looking for a few more digits of precision, looking for a group muon collider there. Uh, so as long as we could do that, because we would need extra digits of precision to see, because then if there was something to that, and we could find a way to hypothetically, let's say, find a closed form for the Planck mass over here, um, then you would be able to predict the mass of the Higgs out to basically all 10 significant digits of h bar. And if you knew more significant digits to h bar, then theoretically you could probably predict it out further. That's the claim. Okay. So we've been going for 46 minutes and I haven't actually even brought up the paper yet. All right. So let's do that now. All right. Let's see. We'll bring up our friend, present screen. This guy. All right. All right. All right. Yes. Yes. So nobody's ever doxed themselves on the internet. All right. So we got an educated guess. And again, this is a rough draft, which is basically the standard calculations that we just went over there and everything. The actual conclusion second, we'll just do verbally here as I've yet to write. Okay. Physics Monastery, Logan, Utah. Okay. I'm going to rewrite. Okay. It's called an educated guess of the Higgs boson mass using the Planck mass and h bar. I know. It's probably. I'm including those for any type of algorithmic searching or stuff. Probably doesn't matter. It's included here. The magnitude between the Higgs boson mass and the Planck mass is approximately 10 to the minus 17. And when squared brings us to a magnitude of 10 to the minus 34. Our measurements put the mass of the Higgs in the realm of 125.11 with error bars of 11 GeV. That was from Atlas 2023, and 125.35 with error bars of 15 GeV from CMS 2022. I have these little brackets just because I'm going to insert the actual notation, citation numbers and everything. All right. It is noticed that the squared relationship between the mass of the Higgs and the Planck mass shows 3 significant digits with corresponding magnitude to h bar. This coincidence is explored, leveraging the 5 known digits of the Planck mass, 7 with error, and the 10 defined digits of h bar to estimate the mass of the Higgs boson to be 125.37 GeV. Oh, I should have error. Oopsie, 21. There we go. See, we're doing it together. So we rise together. I like that saying. Thank you, Stephen. Keywords Higgs boson, Planck mass, Joule second, electro weak. Okay, so we're going to go over our inspiration from alpha. As we had just done, the fine structure constant is defined as alpha equals elementary charge squared over 4 pi, the speed of light, the electric constant times h bar. Where E is the elementary charge, C is the speed of light in the vacuum, E naught is the permittivity of the vacuum, and H is Planck's reduced constant. This important to mention this number is derived from elementary charge squared being divided by that number over there. So when we actually solve for this, what you might say, okay, charge of an electron, charge of a proton, elementary charge squared. Okay, we get some charge, we're squaring it. Okay. What the heck is 4 pi C E naught H bar? Here's what it is. 3.5 times 10 to the minus 36 amperes squared seconds squared. Don't worry, that don't mean a dang thing to me either. But the fine structure constant is dimensionless, meaning this term must be charge squared. Duh. So we take the square root of that, we get 1.8755 times 10 to the minus 18 coulombs. Those that have been doing physics for a little while may recognize that friend as the Planck charge. Taking the square root of this term reveals that equals QP, the Planck electric charge. This means our expression can be simplified to elementary charge divided by Planck charge, square the whole thing. Just like we have over there. Cool. Drawing upon the ability to computationally reduce an expression such as alpha to something more simple allows humans like us to better parse what may be going on in our physical world. Might we be able to employ a similar expression to calculate the constants of nature, such as the mass of the Higgs boson? We employ this method and find a coincidence that appears worth exploring. I probably shouldn't use explore that much. Oh yeah, I forgot that I'll link this little part. It's like the little Wolfram notes. There we go. When you're doing it, they literally just, this is literally the downloaded sheet. This is what you should do. Here's what you should do. And then just go through. All right. Dave, thank you. All right. Magnitude matching uncertainty. The mass of the Higgs has been measured at 25.11 GeV from Atlas and 125.35 from CMS, providing 3 significant digits of accuracy. The Planck mass is calculated to be 2.176434 with error bars of 24 in the last 2 digits. Times 10, so minus 8 kilograms. All right, we got our citation there. And H bar is defined at 1.054 times 10 to the minus 34 joule seconds. We'll do the citation there. We begin by converting the Planck mass to its energy equivalent, E equals mc squared, because we can. All right, so we get that. All right, and then that gives us 1.2208913, and the last 2 digits of error times 10 to the 19 giga electron volts. Okay, so the Planck energy, E sub P, is equal to that number there. We construct our equations. 5A using Atlas 2023 and 5B with CMS. So basically, we're just taking the measurements. We're going to get a look at it. Okay. So this gives us over here, when we do Atlas, I should probably label these better, but 5A. Okay. You got that number there, 1.0501. Error bars of 19. And then we get 1.054 with error bars of 26. And the last 2 digits we have here, times 10 to the minus 34. Okay. Next, we conjecture that our output should be the magnitude of H bar. We place our value for the Higgs mass with, oh, hold on, that should be a tab. Because that's what you're supposed to do. What are we in? What are we at? Oh, format, face. There we go. Much better. See? Progress already. Helps actually doing the thing. I'm not sure if Rick had popped in at all yet, but thank you, Rick. I did get your LaTeX layout and everything. That's going to make things so much easier. Thank you. All right. Higgs mass with X and solve. Hold on. We replace our value for the Higgs mass with X and solve for giga electron volts because we're solving for energy. Here we invert our equation. So basically, rather than doing the Higgs mass, or excuse me, the mass of the Higgs over the Planck energy, we're just going to do the Planck energy over it. I think it looks prettier multiplying by H bar than dividing it. Again, personal preference. All right, so we take our Planck energy over here, and now we're going to divide it by X GeV. So we're going to solve for X, and we square it like we did before. We're multiplying by H bar, Planck's reduced constant, and we're setting it equal to a 1. That 1 happens to be 1 joule second. Okay. Solving for X results in positive and negative values, as we have over on the board there. 125.37 GeV with error of 21 in the last 2, according to the values we have. And we have that as a positive number and a negative number there. Okay. Okay. And this is about all we have, right? Okay. We have got figures in display. So let's do this. Okay. So here are the this is from Atlas. I believe this is 2023. Okay. So I think they have their earlier runs for the previous years, and then they have the more recent ones combined. Okay. So the Higgs masses also come in at, all right, we got 126 GeV plus or minus 50, 124.51 plus or minus like 52 there, 125.17, 124.99, 125.22, and as we can see, 125.38. That's really close to our number there, in the 25, 10, and then the current world average here is 125.11 plus or minus 11 giga electron volts there. Okay. Okay, so that was 2023 combined results. And this is the CMS preliminary that we have over here. So this, okay, so then they had, I mean, it does say, okay, is that just, why is it listed as 2022? Did I take the wrong one? Okay, I may just need to. Oh, this does come from because I've gone through this before. Okay, I'm gonna need to look more into explaining what the heck I'm talking about. Long story short, different experiment, but they're looking for the same thing over here. Okay, 124.7, 125.59, 125, 125, 125, 125, and then this is the number we're using, combining it here. That seems to fall quite well within the measurement there. It also happens to is that 125.35 plus or minus 15? 125.35 GeV, 125.37 GeV. Seems to be within the error bars. But yeah, that's basically really what we've got here. I mean, it's nothing fancy, and to be fair, if ultimately if we wanted to get something like 14 digits of the Higgs one, we're going to need to measure it out to at least like 10 or so significant digits. Why am I saying 10 or so significant digits rather than 14? Well, obviously, we need to measure it to 14 in order to get to 14. Unless hypothetically, um, two things. One, we would need to know at least 14 digits to the Planck mass, aka, or the Planck energy, to be more precise in this format here. Does anybody have 14 digits for the Planck energy? I mean, we only have the speed of light to, to actually 9 significant digits, or maybe 10 if you include the zero there, fractal and put it in. I'm pretty sure it's 0. But we have it measured, again, two-way speed of light is how we're actually doing it, but it's measured to 9 significant digits. Okay. Hypothetically, if we had a closed form where we could get all the digits for the Planck mass and H bar, we could actually try to predict the Higgs boson mass out there. Now, there's nothing within the literature, to my knowledge, that has that. Maybe there is. Maybe there actually, to be fair, I'm sure somebody's done a calculation. Is it on CODATA? Is it being used? No. That's the thing. Now, again, I'm perhaps coming from a very biased position here, but if we were to be able to find something like that, then we could calculate it. And to be fair, we would actually need measurements as well, I would claim, because at least with what we've been doing for a lot of stuff here at the Physics Monastery is we're basically finding that there appears to be a partition. Some may say a product, maybe some Cartesian planes, if you would. I'm stealing that from Professor Jacob Barondis, because apparently that was in one of his slides that he's been giving. Apparently, he found that he may have broadened the axioms of quantum theory. by finding that, okay, we assumed we had to use Markovian dynamics and stuff. Okay. He was actually using a non-Markovian process by accident, but that may be one of the most happy accidents of recent time because it appears as if that happy accident, he's able to rederive the base axioms of quantum theory in that, listen, you can use an infinite dimension Hilbert space as your configuration space, but you don't necessarily need to do that. You don't necessarily need to use an infinite dimension Hilbert space or wave function to model the things because it's within the non-Markovian process. I believe it's the key word is unistochastic. It's like stochastic. That sounds like billiard balls. Yes, it sounds like that. What if you had all the dynamics? You may go down as the man that took all the fun out of quantum theory. Where'd our woo go? You've got your beatables, and now we're able to start going through emergibles, and now we're able to do this and that. And God, what about Schrodinger's cat? Won't somebody think of the crazy imaginary kittens? Ah, I don't know. I've seen a cat that seemed to be awake and asleep at the same time. That's my response to Professor Carroll there. Oh, what the heck was I doing? Oh, I was bringing up. Let's do this. I believe. I think it's this guy. Let me see. Dun, 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 dun. Okay. And that is, I'm just bringing, where is that? It should be the length and time. Okay, I think it's this guy. Okay. So not that anybody's keeping track, but hypothetically, at least according to some current calculations, uh, this guy. Okay. Hypothetically, if we had, let's say, a closed form for the Planck mass, and oh, maybe we just did this calculation to find its mass. Okay. Okay, so if we happen to have a closed form for the Planck mass and we were going to solve for x, and we happen to have like 14, 15 digits for h bar, and we were to set it equal to 1, we may get a mass unit out of, I don't know, again, a negative antipotomy. It's a 2.2350, 238054810 times 10 to the minus 25 kilograms. And we have that as kilograms, and we multiply that by our dimensions of length and time squared, and then we put in the mass energy correction factor that we have on the poster there. Don't worry, nobody should actually know what any of that stuff means unless you've actually gone through and binged all these things and probably practiced with the calculations. But that would give us an estimated mass of the Higgs if there wasn't another second piece or something to it. Or to be fair, I may have just put in numbers for the second piece. Hypothetically, 125.375640590077 approximately giga electron volts, or the mass of the Higgs. But again, that's conjecture on my part. So, but that's all we really got. So yeah, we were able to do the paper in about the last 15 minutes there. And now, and hey, we're even over time and everything as other folks have joined us. But that's all we got for right now. So just a quick recap. We take inspiration with a computationally reduced form of alpha. So we go from the fine structure constant second equal to elementary charge squared over 4 pi h bar c e naught. We can computationally reduce that into elementary charge over Planck charge. We square the whole thing. Using that inspiration, basically just take the mass of the Higgs divided by the Planck mass, square the whole dang thing. We get the first 3 digits and magnitude of h bar, the elementary unit of action. So we entertain the idea, maybe it is supposed to come out as the magnitude of h bar, as a missing puzzle piece, so to speak. So we invert it, convert it to its energy equivalent. This is strictly for prettiness, in my opinion here. So we get the Planck energy, and we're going to be solving for x, giga electron volts, because this is in energy. We have the same squaring like we've done there. And in this case, since we're solving for x, we multiply it by h bar, and we set it equal to its unit of 1, which is 1 joule second. And when we do that, we get out an estimated mass of the Higgs of 125.37 GeV. We get our error bars of 21 in the last two based upon our calculations and the calculated and defined values of h bar and the Planck mass. And that compares to, we got Atlas 2023, 125.11 gigaelectron volts with 11 error in the last two digits, and then the CMS 2022, 125.35 gigaelectron volts with error of 15 in those last two digits there, compared to our conjectured value that we calculate here of 125.37 GeV with error of 21 in the last two. So again, we're going to need to have higher precision measurements to be able to get out a few more significant digits, help increase our accuracy, so we can either cast this aside, this is falsified, or maybe it bears out a little bit more. But we're going to have to wait and see what happens. So that's about all. But everybody, take care of yourselves. We'll work on this over the weekend. And other than that, take care, everyone. The crazy.